Welcome back to Lesson 9 of our overview of the course Networks and Distributed Systems using the textbook by Jim Caros and Keith Ross, Computer Networking, a Top-Down Approach, 6th edition. In the last lesson we were talking about delays. Let's pick up where we left off. The delay and packet loss are very important factors to use in evaluating network performance. Another factor is the rate at which data can be transferred from source to destination. This is called throughput. The amount of data that can be transferred across a link during a certain period of time would be throughput. The importance of throughput depends on the application. For example, if one's downloading a book to read, the time it takes for that book to arrive is not all that critical. As soon as it's here, we can begin reading, whether that was 1 minute or 15 minutes from now. On the other hand, if you're watching a movie from one of the popular movie services online, slow throughput can be a real problem. You've dealt with this, haven't you? You're trying to watch a movie and every few seconds it stops with some sort of spinning wheel on the screen. Your problem may have been a number of things, one of which might have been poor throughput. By the way, what we're seeing in this slide is that traffic is flowing in both directions on the link, and obviously the throughput to the link affects the flow in both. Remember a few slides back our discussion of the conversation taking place between hosts at each end. How about the effect of poor throughput on an online group conference? Would it be a problem? Certainly it would. Like using an internet phone service, this performance would be much worse than inconvenient. Of course, in the grand scheme of information importance, these examples would be trivial. There are many other examples where slow throughput would be considered mission critical or even life or death. However, that said, it's important that we understand that this is just one of the factors of concern when it comes to network performance. Our goal is to address the whole problem, and when we're doing that, we find that there are trade-offs. Usually the solution must be evaluated along with the cost. Network performance will be impacted by the arrangement of links from end to end. Also, it is true that the performance issues are most prevalent at the access networks, our company or our university networks. Also, these autonomous networks are the ones we can control. It's in these networks that we concern ourselves with problems like the one shown here, bottlenecks. In general, those hosts and links that make up the backbone of the network have very high capacity and performance specifications. Here we see a graphic depicting the issue of bottlenecks. You'll note that the networks S and C are viewed as the sources of bottlenecks in this network arrangement. From our discussion thus far, it's apparent that the Internet is an extremely complicated system. We have seen that there are many pieces to the Internet, numerous applications and protocols, various types of end systems, packet switches, and various types of link-level media. Those of you who have taken a business course have probably heard of the general systems approach to problem solving. In a nutshell, the general systems approach suggests that the way to solve a very complex problem is to break that big problem into much smaller and more manageable pieces. To provide structure to the network's protocols, network designers organize those protocols and the network hardware and software that implement the protocols into layers. In other words, they're implementing a general systems approach to solve the very complex problem of networking. Each protocol belongs to one of the layers. We are interested in the services that a layer provides to the layer above it, the so-called service model of a layer. Consider the first layer being at the top where an application is making a request from its counterpart at the other end of the network. In other words, your email client is asking for something from an email server. A protocol layer can be implemented in software in hardware or a combination of the two. Each layer provides a service by performing certain actions within that layer and by using the services of the layer directly below it. That email application, for example, may be great at its application layer job, but it doesn't have a clue how to verify that a packet sent from one switch is guaranteed to make it to another switch. It can honestly say, that's not my job. Moving packets from switch to switch is the responsibility of another layer in the protocol stack. This layer, therefore, must request services from the next layer. Before the collection of tasks is done, the process will make it through miles of wire and many switches and probably many routers, which will require action of all the layers before the task is complete. That request makes its way from layer to layer and protocol to protocol until the job is done. A layered architecture allows us to examine a well-defined, specific part of a very large and very complex system. This simplification itself is of considerable value by providing modularity, making it much easier to change the implementation of the service provided by the layer. As long as the services to the layer above and the services from the layer below are not changed, modification of any layer's implementation can be made without any effect on the rest of the system. When taken together, the protocols of the various layers are called a protocol stack. The Internet protocol stack consists of 5 layers: the application layer, transport layer, network, link, and physical layers. This course is organized by using the layers of the Internet protocol stack. We take a top-down approach, first covering the application layer and then proceeding downward. The application layer is where network applications and their application layer protocols reside. The Internet's application layer includes many protocols, such as HTTP protocol, which provides for web document request and transfer. FSMTP, which provides for the transfer of those email messages we were just discussing. And FTP, which provides for the transfer of files between two end systems. We will see later that it is very easy to create and deploy our own application layer protocols. An application layer protocol is distributed over multiple end systems, with the application in one end system using the protocol to exchange packets of information with the application in another end system. The Internet's transport layer transports application messages between the application endpoints. In the Internet, there are 2 transport protocols, TCP and UDP, either of which can transport application layer messages. TCP provides a connection-oriented service to its applications. This service includes guaranteed delivery of application layer messages to the destination and flow control. Flow control is sender-receiver speed matching. Routers can function at different speeds, and therefore there has to be some mechanism to allow them to coordinate their combined abilities. TCP also breaks long messages into shorter segments and provides a congestion control mechanism so that a source adjusts its transmission rate when the network is congested. UDP protocol, on the other hand, provides a connectionless service to the applications. This is a no-frills service that provides no reliability, no flow control, and no congestion control. The biggest difference between the two is that TCP is guaranteed and UDP is not. Usually the package generated by a transport layer is referred to, by the way, as a segment. The Internet's network layer is responsible for moving network layer packets, known as datagrams, from one host to another. So that transport layer segment became a network layer datagram. The Internet Transport Layer Protocol, UDP or TCP, in a source host passes a transport layer segment and a destination address to the network layer, just as you would give the Postal Service a letter with a destination address on it. The network layer then provides the service of delivering the segment to the transport layer at the other end. The Internet's network layer includes the IP protocol, which defines the fields in the datagram as well as the end systems and the routers act on these fields. There is only one IP protocol, and all other Internet components that have a network layer must run the IP protocol. The Internet's network layer also contains routing protocols that determine the routes that the datagrams take between sources and destinations. The Internet has many routing protocols. The Internet is a network of networks, as we've said before, and within a network, the network administrator can run any routing protocol desired. Although the network layer contains both IP protocol and numerous routing protocols, it is often referred to simply as the IP layer, reflecting the fact that IP is the glue that binds the Internet together. The Internet's network layer routes a datagram through a series of routers between source and destination. To move a packet from one node, a host or a router, to the next node in a route, the network layer relies on the services of the link layer. In particular, at each node, the network layer passes the datagram down to the link layer, which delivers the datagram to the next node along the route. At the next node, the link layer passes the datagram up to the network layer. The services provided by the link layer depend on the specific link layer protocol that is employed over the link. For example, some link layer protocols provide for reliable delivery from transmitting node over the one link to receiving node. Note that this reliable delivery service is different from the reliable delivery service of TCP, the transport protocol, which provides reliable delivery from one end system to another end system. The link layer is providing reliability from one node to the next node, one link. Examples of a link layer protocol include Ethernet, Wi-Fi, and the Cable Access Network's DOCSIS protocol. As the datagrams typically need to traverse several links from source to destination, a datagram may be handled by a different link protocol at different links along the route. For example, a datagram may be handled by Ethernet at one link and by PPP on the next link. The network layer will receive different service from each of the different link layer protocols. In this course, we'll refer to the link layer packets as frames. While the job of the link layer is to move entire frames from one network element to an adjacent network element, the job of the physical layer is to move those individual bits that make up those frames from one node to the next. The protocols in this layer are again link dependent and further depend on actual transmission medium of the link. For example, twisted pair, copper, or single mode fiber optic cable. For example, Ethernet has many physical layer protocols, one for twisted pair copper wire, another for coaxial cable, another for fiber, and so on. In each case, a bit is moved across the link in a different way. Well, this has been a very long lesson, so let's take a break and evaluate what all we've seen and heard, take care of any assignments we may have, and after you're recuperated from it, come on back and we'll proceed to the next one.